So more examples using triangles. So we have a lighthouse. The lighthouse is here, and it's 400 feet tall. Okay. The radius of the Earth, which we're going to pretend is a sphere, it's close, but it's not exact. But the radius of the Earth is 3,960 miles. Okay. So the light beam from the lighthouse is 400 feet taller than that. Now, light emanates in all directions from the lighthouse, but if you're at a certain point on the Earth, maybe you don't see the lighthouse because all the light beams are blocked. So what we want to see is how far away, and we're going to pretend this is a straight line, okay, how far away on the Earth do you have to be before that lighthouse disappears from sight, before you can no longer see its beams, assuming that your head is exactly on the surface of the Earth. Okay. So the way this problem is phrased, there's a claim that you can see the lighthouse from 26 miles away. Is that true? So let's find out. So we're going to put theta down here. Now the geometry at play is that this line from the lighthouse is tangent to the circle. It just deflects right off the edge. And lines tangent to circles are perpendicular to radii of circles. So there's your right angle. And this is the angle theta. Notice that this side is exactly 3960. This side is just a little bit longer. I have miles, I have feet. So we're going to convert everything into miles. Okay. It doesn't really matter whether you convert to miles or feet. The numbers would get quite large if you worked with feet. So this extra 400 feet, we're going to convert to 400 out of 5280 miles. So the cosine of theta is very, very, very close to 1. Now the number of decimal points or significant figures becomes important, because if you were rounding this off to 4 decimal points, you would just round this off to 1. And then the cosine of theta is 1 means the angle is 0, which, okay, it's really close to 0, but it's not exactly. So we need to be pretty precise here. So we're going to use more than 4 decimal points. Okay, so solving this for theta is the arc cosine of, that's actually wrong, of 0.999980870. They're just taking the arc cosine of this, okay, which is very, very small. Okay, this is a typo. Those should have all been 9s, those leading 4 things. This is very small. It's 1/3 of a degree, okay, which you can convert to minutes and seconds. Very few people would actually do this, but fine. We have 21 degrees and 27 minutes. Sorry, 21 minutes, 21.27 minutes. If you're the type of person who converts from degrees into minutes and seconds, I'm not sure why I didn't further convert this into seconds. Most people would actually just leave this as 0.35440 degrees. But in any case, we now have the angle theta. Okay. So there is a difference between miles in how most people refer to miles. Those are statute miles versus nautical miles, which is how people on boats measure miles. They're different units, because why would we use the same unit when we use the same name? So the benefit of nautical miles is that 1 nautical mile is exactly 1 minute of an angle traced out on the Earth's surface. So you can imagine if you're on the Earth and you're actually doing like long ocean voyages, and you don't have landmarks like mountains or whatever to measure off of, these angular measurements are really a nice natural way to measure how far you're traveling. So a nautical mile is exactly 1 minute of angle from the Earth's center. So since we had determined this was 21.27 minutes, it makes it 21.27 nautical miles. Let me erase my pictures. Okay. In statute miles, we would use this formula where the arc length is the radius times the angle. Okay, remember that from way back when. So we have, but remember that formula requires radians. So we convert our 0.3544 degrees into a very small quantity of radians, but it does get multiplied by a rather large radius, and we get 24.5 statute miles. So the brochure said 26 miles, which is a slight overestimate. Okay. No, this was what? It was 21 point something nautical miles. So a nautical mile is actually a little bit longer than a statute mile. It was only 21 nautical miles compared to 24 point something statute miles. And when you hear boats having their speed measured in knots, that's nautical miles per hour. So a boat going like 15 knots is actually going slightly faster than 15 miles per hour. And the difference is just, are you doing miles or are you doing nautical miles? Statute miles are traditional miles. They're 5,280 feet. A nautical mile is just what is drawn out on the surface of the Earth by an angle of 1 minute. Anyway, that's that example. Okay, next example. Suppose we start at O, and we are going to go towards P4. Okay. So what's the bearing? What angle do I need to go to get to P4, given everything that's marked here? So, pardon me. What you do to get your bearing is you, this angle here was given at 20 degrees. So the way bearings are spoken, and again, this is like technical jargon. Don't worry about this. If you just drew this figure and said go that way, that'd be fine. This is like a boat navigation speak. This isn't really how we talk about directions and math. You would say from south, you go 20 degrees east from there. So from south, you go degrees in the eastern direction, and that's going to point you at P4. This is just telling us how to describe bearings. Okay. So suppose a aircraft takes off with a bearing of north 20 degrees east. So instead of going straight north, it's 20 degrees further east than that. After flying for 1 mile, okay, the aircraft is going to turn 90 degrees and go northwest. So after the plane goes 2 miles in that direction, what's the bearing from the control tower? So the first thing we want to do is draw this picture. Okay. So we started going 20 degrees. So this was the original bearing, north 20 degrees east. So from north, go east 20 degrees. So that's how we start. After 1 mile, we exactly turn 90 degrees left and go 2 miles. So now we're at this point, and the question is, what is this bearing here? So here's what we've got. We've got a length of 2, a right angle, a length of 1. And what we want to determine is, what's this angle here? But we actually know that this angle is 20 degrees. So if we can just find the missing angle in the triangle and take away 20 degrees from it, we'll know what our bearing is. It's that many degrees west of north. Okay, so let me clear this so we can see theirs. So if we look at the angle theta, which is this entire angle, okay, opposite 2 over adjacent 1. Remember, look at the information you have and determine which trigonometric ratio is appropriate. So if you're going to try to solve for this angle down here, what you have is the opposite side and the adjacent side. What you don't have is the hypotenuse. So tangent is the relevant trig function. So that makes theta the arctangent of 2. Again, if you want to round this off, it's fine. If you want to just call it arctangent of 2, that's great. But we know we actually want to take away 20 degrees. So that leaves behind 43.4 degrees. So that's our bearing. From north, 43.4 degrees west of that. Okay. So that's it for this slide. Don't worry so much about those nautical and whatever terms. We're just going to measure angles in degrees and call it a day. We're going to measure distances in whatever units we want. Miles, nautical miles, kilometers, honestly, would be the most common thing. I'm not sure why the book hasn't given us a single example in metric units. But don't worry about units and unit conversions and all that. It's not going to be the focus. It's really solving triangles. Okay. So in the next section, we're actually going to start working with triangles that are not right angles, but you can still use trigonometry to do it.